Hello! Today we're going to be talking about matching complexes. My name is Fran and this is Legrand.
Graphs are often used in computer science to represent data points and relationships between data points. Here, graphs will just be dots and lines connecting them. A matching of a graph is a set of edges in our graph such that no two share an endpoint. So in our picture at the bottom, the pink are matchings of our graph. A matching complex is the set of all matchings of a graph and can be visualized as a simplicial complex. So at the left, we have matching 1, 3, 5, and at right, that's represented by the triangle 1, 3, 5.
One natural question we can ask is what happens if we take the matching over and over? Well, there are a few different possibilities. First, the graph could dissipate. This means that at some point down the line, we get the empty set. It is also possible for the graph to stabilize, where we continue getting the same result out of the operation. Finally, it is possible for the graph to blow up. As we continue taking the matching, the number of edges and vertices in the graph grows without bound. Our goal surrounding this idea is to characterize the behavior of taking iterated matchings of a graph, based purely on properties of the initial graph. We have been approaching this question by considering the dissipation number, or D value of a graph. This is the number of matchings it takes before the graph dissipates, or arrives at the empty set. In this example, D equals 4 because we perform the matching operation 4 times before we get back to the empty set. If the graph stabilizes or blows up, then we say D equals infinity. There are 2 special cases to consider, this pentagon on the left and this triangle with 3 pendant edges on the right. These are the only 2 graphs that return themselves after the matching operation. Our conjecture is that every graph with an infinite D value eventually accumulates one of these 2 special graphs as a subgraph. We have confirmed this for various well-known families of graphs.
Another thing we've been attempting to find is the intersection of all matching complexes and all 2D Buxbaum complexes, where 2D Buxbaum complexes are a type of simplicial complex that come up in other areas of math, including topology and algebra. For us, 2D Buxbaum complexes are defined by being constructed by piecing together filled-in triangles and having a local connectedness condition. So our example at the left is a 2D Buxbaum complex, while at center, the local connectedness condition fails. Particularly, we've been finding success with attempting to construct all graphs whose matching complex is a 2D Buxbaum complex. One such family of graphs is BC4 at right. So we're on our way to proving our conjecture at the bottom.
Thank you for listening, and I hope that we can answer any questions you may have.